Okay, now alkanes is the simplest functional group in organic chemistry. For some, it's not even a functional group because of the fact that almost every single organic molecule possesses a portion of it which is an alkane. All right. First, you need to know that they are saturated, which means that they are only made up of sigma bonds, and you need to know their general formula is CnH2n plus 2, where n is greater than or equals to 1. All right. So guys, I will go to the chem guide first, all right, and take a look at what is required as an IB student for this particular chapter. Now, this particular chapter talks about how a radical is formed, okay, and how radicals are being produced when you react with a halogen. And we talked about substitution reactions with alkanes producing a mixture of products. Okay, so there are three learning objectives that we need to cover in this particular chapter. Is that clear? Okay, so we go back to our lecture notes again. Now, first, if you notice, one of the learning objectives is to understand why alkanes are so unreactive. Okay, they are literally like Switzerland. They are a neutral compound. They have no reason for them to be attracted by an electrophile or even a nucleophile. And why is that so? It is because of the fact that if you take a look at methane, the electronegativity difference between carbon and hydrogen makes them, the small electronegativity difference between carbon and hydrogen doesn't allow for the formation of this delta plus, this is not around, or delta minus also not around. So as a result, there is no reason for an electrophile, i.e. electron deficient species, or an electron rich species to be approaching this particular molecule. Clear? So as a result, this molecule here is unreactive. So that's the first reason. The first reason is written here in bold due to the non-polarity of the CH bond, since C and H are very similar in electronegativity. The consequence of non-polarity, guys, is that the nucleophile nor electrophile will be attracted to you. This is compounded, all right? There's a second reason. This is compounded by the fact that the CH single bonds are very difficult to break. Clear? And because they are very, very difficult to break, it makes them unreactive. Now, if you go to your data booklet, guys, CH bonds has a bond energy of 413 kilojoules. UV light can't really break these particular CH bonds. They need additional help from your heat, for example. Is that clear? Now, let us take a look at some of the physical properties of alkanes. Now, melting and boiling point increases as you go down the homologous series, because down the homologous series you increase by a CH2 group, so the size of electron cloud becomes larger, and when your size of electron cloud becomes larger, your London dispersion forces becomes larger. In this lecture notes, they mention about instantaneous dipole-induced dipole. That in IB terms is known as London dispersion forces. So more energy is required to overcome the intermolecular forces of attraction. Is that clear, guys? Next up, we shall carry on to what happens, okay? All right, so what happens when you are isomers? All right.
Wait, so if you put ID instead of...
Or both are accepted.
Okay.
But London dispersion forces is in their answer key. Okay? Now, so if you take a look at these two isomers, right, they will have the same electron cloud. Correct? Agree? Because they have the same MR. If they have the same MR, means they have the same electron cloud size. Clear? However, these two are what we call as aliphatic molecules. You still remember not the term we used last week? Aliphatic, which means that you are either straight or branched. Correct, not? So, when you are a straight chain hydrocarbon, there's a greater surface area of contact. With a greater surface area of contact, therefore your London dispersion forces are stronger. The molecule in green, right? You do realize that they have a smaller surface area of contact, with a smaller surface area of contact, their London dispersion forces is less extensive and hence lower boiling point. Now, please remember, you can only compare degree of branching, degree of branching when it is a non-polar compound. Alright, we are talking about non-polar components, and we realize that the size of electron cloud is the same because they are isomers of each other. Then you can talk about degree of branching.
What's the degree of branching?
Whether you are straight or you're branched.
Okay.
So the more branched your molecule is, the lower the London the less extensive the London dispersion forces. Hence, the lower the boiling point. All right.
For larger surface area.
Sorry.
Larger surface area.
Larger surface area means more extensive London dispersion forces. More extensive London dispersion forces translates to more energy required. More energy required translates to higher boiling point.
But then you said like we can only talk about degree when it's
Non-polar.
non-polar.
Yeah.
So these are non-polar.
Yep.
Okay.
Solubility. Okay, for solubility, because they are non-polar compound, they dissolve very well in non-polar solvents. All right. Now we shall move on to the first chemical reaction of alkanes. Not very important. We call it combustion of alkanes. There are two types of combustion. Number one is complete. The other one is incomplete. Incomplete combustion will result in in four different products. You have soot, i.e. carbon monoxide, carbon dioxide, and water. Understand, guys? Okay, so four products of incomplete combustion. When you're dealing in complete combustion, you will get only carbon dioxide and water. Now, the next part is where the important portion is, which is the whole chapter, which revolves around this whole subtopic. So if you take a look at this particular reaction, this is called a halogen. X2 is a halogen. This is what we call as inorganic. Alright, inorganic species are responsible to determine whether you are free radical, you are a nucleophile, or you are an electrophile. The organic molecule will determine whether you are undergoing the 7 different types of chemical reactions. So like addition, substitution, hydrolysis, the organic molecule is responsible for telling you that. So therefore, guys, if you take a look at this word free radical substitution, this is determined from the inorganic portion of the reactant. So this is the inorganic reactant that will tell you. Substitution is from the organic reactant. Understand, guys? So if you take a look, let's start off with the organic compound, shall we? The organic compound is very, very clear cut that he is saturated. You all know what is saturated, right? Means made up of sigma bonds. Only sigma bonds. Understood? So because he's only made up of sigma bonds, for him to undergo a chemical reaction, one atom has to leave for another to come in. And in chemistry, we call that substitution. Now, the inorganic reagent in this case is chlorine. Alright? Or X2, which is a halogen. Now, when methane approaches chlorine, because he is saturated, there will not be any effect or minimal effect on the electron cloud of chlorine. And because there's minimal effect on the electron cloud of chlorine, guys, okay, chlorine will break up homolytically. Let's break down the word. What is the word homolytically? Which means that they are sharing 2 electrons. What happens is they will break up. Each chlorine atom will receive 1 electron each. So the chlorine on the right will receive 1. The chlorine on the left will receive another 1. So 2 electrons, 1 go to each chlorine atom. And because they receive the same number of chlorine atom, we say that it is homo, which is in Latin is same. Lytic comes from the word lysis, which is breakdown. Fission means I need energy for this. Are you all clear now? So the word homolytic fission, homo means each particular atom receive the same number of electrons. Can? Lytic means break apart. Fission means I need energy. And this energy comes from where, guys? UV light. Now, guys, because of the fact that you break apart to give you each atom receive 1 electron each, you produce this particular species called a chlorine-free radical. A chlorine-free radical is a neutral species. It is not charged. Are you able to see that? It is a paramagnetic species that you learn from transition metal. Paramagnetic are species that has an unpaired electron.
Wait, I have a question. Why is the electron cloud of CH4 not affecting Cl?
Because of the fact that CH4 is not electron rich. However, if you have an alkene, for example, look here. If you have an alkene, when an alkene approaches chlorine, it will cause the polarization of the chlorine molecule. Are you able to see that? Can you see the difference between an alkane approaching chlorine and when an alkene approaching chlorine? When an alkene approaches chlorine, it causes the polarization of the electron cloud, instilling a delta plus and a delta minus on the chlorine atom. So when they break up, when the chlorine atom over here breaks up, they're going to break up heterolytically. Can you see that? So this is for alkenes. Alright, I know that I haven't gone into the chapter alkenes yet. I just want to highlight the difference. Even though the controlled variable is chlorine, but when alkene reacts with chlorine is different from when an alkene reacts with chlorine. And the main difference is because alkene is electron rich. And when you're electron rich, when you approach the chlorine molecule, it polarizes the electron cloud of chlorine to this side. In layman term, it distorts the electron cloud of chlorine, inducing a dipole. Can you see that? It induces a delta plus and a delta minus. So when chlorine undergo a fission or lysis, it undergoes heterolytic. The chlorine atom on the left receives 0, while the chlorine atom on the right receives 2 electrons. And because you receive differing number of electrons, 0 and 2, therefore in Latin we call it hetero. So it's called heterolytic fission. Now, when you do heterolytic fission, you always get a product of an electrophile as well as a nucleophile. So you need to commit to memory. Homo fission, radical. Hetero fission, you're going to get an electrophile and a nucleophile. Understand, guys? So if you take a look at your products, you realize that there's an electrophile and a nucleophile. You know that the reactants underwent hetero fission. When you see that the products are radicals, you know that they underwent homo fission. Clear?
Radical is just an inorganic.
Sorry?
Radical
Radical is an unpaired species. And a species that has an unpaired electron.
Wait, so homo fission is when they break up?
Yeah. They break up and each particular atom receives 1 electron.
That's hetero.
That's homo.
Oh, that's homo.
Yeah.
Oh, then hetero is...
They break up, one species receives absolutely nothing. The other species receives 2 electrons. So the species that receives 2 electrons has made a profit of 1. Because at the start of the relationship, each atom contributed 1. At the end of their relationship, he got 2. So what's his net profit? 1 electron. And that's the reason why you get Cl minus. Can you see Cl minus? Because he made a profit of 1 electron, what? The Cl plus is formed because he contributed 1 at the start of the relationship to form a covalent bond. At the end, he received nothing at all. And that's why he is Cl plus. Now, let's check whether or not he is electrophilic. Alright, to check whether someone is electrophilic, you either draw the Lewis structure, should it be a molecule, or you write the electronic configuration if it's an element. So if you take a look at Cl plus, it is 3s2 3p4. Can you see that or not? 3s2 3p4. That basically tells us that he is short of how many electrons, guys? 2 electrons to reach that octet configuration. Agree not? 2 plus 4 is 6, right? 3s2 3p4, 2 plus 4 is 6. So he needs 2 more electrons. So which means that he himself, Cl plus, is electron deficient. At the same time, because it's 3p4, he has available orbitals to accept the lone pair of electrons from a nucleophile. So for you to be an electrophile, guys, you need to take note of 2 things. Number 1, you need to be electron deficient, as you can see from Cl plus. He is electron deficient, right? Number 2, you need to be able to accept the lone pair of electrons. Means you need to have something to accept those lone pair of electrons from a nucleophile. And who houses electrons, guys? Orbitals. So if you got no orbitals, even if you are electron deficient, you cannot receive what? Clear? So that's why for you to be an electrophile, you need to meet these 2 requirements.
So hydrogen can't.
Hydrogen plus can. H plus is 1s0, so he has an orbital to accept. H is a radical because it's only one electron. H minus is a nucleophile because he has two electrons with a negative charge.
Wait,
Clear?
so then, like Na plus, it can't be because the gap is too big, is it?
Na plus, if you write down the electronic configuration of Na plus, you do realize he is not even electron deficient. He has that octet configuration. That's one. Second, should he want to use his orbital, the next available orbital is at 3s0, which is energetically inaccessible, because you all learn from the hydrogen emission spectrum in chapter 2 that the gap between level 2 and level 3, principal quantum shell 2 and 3, is pretty large. And because it is large, it is energetically not feasible for me to use his 3s orbital unless I'm being supplied with large amounts of energy. And as a result, Na plus is not an electrophile, even though he has a plus sign. So the learning point here is not everything that has a plus sign warrants you to be a electrophile. So you cannot make sweeping statements. Everything that has a positive charge confirm will be an electrophile. You must go on a case-to-case basis. Check. If it's an element, write out the electronic configuration. If it's a molecule, draw the Lewis structure
Wait, can you show us an example?
of a molecule. H3O plus.
Ah,
So if you take a look at H3O plus, he is neither a nucleophile. Why? Because despite having a lone pair, he is positively charged. So when he approaches the nucleus, because he's a nucleophile, right? Means he loves the nucleus, correct or not? The nucleus is positive, will be repelled by the positive charge. So therefore, he doesn't meet the requirements of a nucleophile, even though he has a lone pair. Number two, he can't be an electrophile either, because he has 8 electrons around him. Are you able to see the 8 electrons around oxygen? So he's neither electron deficient either. So as a result, he's not electron deficient, he's not electron rich. So therefore, he's neither a nucleophile nor an electrophile. Clear on this?
wait, so why can't he donate his lone pair as the lone pair?
Because got plus charge. As he approaches the nucleus, he'll get repelled.
Oh.
Because the nucleus is positive charge.
Wait, so is this called a free radical?
No. A free radical is any species, whether a molecule or an atom that has an unpaired electron. So IB, your syllabus has really, if you take a look at right at the top, is a molecular entity that has unpaired electron. Can you see that? No? That's the definition of a radical. In short, molecular entity, you can replace it as a species lah. Alright guys? Can? Okay.
Wait, but then in this case, like this reaction, how is chlorine a radical? If it gains electron from...
In this particular reaction with alkene, he is not a radical. When he is with an alkane, he forms a radical.
Well, I thought he gains the electron, then he wouldn't have any other...
What do you mean by he gains an electron?
I thought you say like...
You see, chlorine right now, right, have 6 electrons around him. Do you agree or not? If I draw my lone pair, after the breakup, he received 1 electron. Wouldn't that make from 6 become 7? So he has 7 electrons, right? 7 electrons is odd. So therefore, it is a free radical.
So like the electrons they share is just gone when the bond...
When the bond breaks, the shared electrons, 1 will go to each species. Does that make sense or
So
not?
that's the electron that you're talking about?
Yes, correct.
Wait, then it's not electron deficient because O is already at octagon.
Very good.
Okay.
Mm.
Understand.
O already has 8 electrons around him.
Yeah.
So neither electrophile nor nucleophile.
Yeah.
Understand not?
Yeah.
Okay. So must be very careful to take a look at who is an electrophile and who's a nucleophile. Understand? So sweeping statements for nucleophile will be anyone that has a lone pair is a nucleophile. That's not a true statement, yeah? Okay, you need to be neutral or negatively charged and has a lone pair of electrons. In the last lesson, I also illustrated the difference between a ligand and a nucleophile. Correct or not? A ligand donates to who?
Central atom.
Central metal atom or ion. Very good. But a nucleophile donates to electron deficient carbon atom. But what's the common thing between a nucleophile and electrophile? It came out in 2021. Yeah. What's the common thing between a nucleophile and a ligand? My bad.
Electron pairs donated.
Yeah, they are both electron pair donors. And electron pair donors are also known as what? In the chapter of acids and bases,
Lewis acid.
they are Lewis bases. So a nucleophile and a ligand are both Lewis bases. Are you all clear on this? That's the common denominator between a nucleophile and a ligand. Alright, the only reason why we name them differently is because they give their lone pairs to differing species. Okay, now going back. So I do hope later, when next lesson, right, when I talk about alkenes, guys, okay, I do hope that y'all will be able to appreciate why alkenes undergo heterolytic fission of the chlorine molecule, while alkanes undergo homolytic fission of the alkane molecule. Because of the fact that alkenes are electron rich, it can polarize the electron cloud of chlorine to a greater extent, and therefore it can induce a dipole on the non-polar chlorine molecule.
So you said nucleophile must be neutral or negative.
Negatively charged that has at least one lone pair of electron. That is on page 17.
Wait, can you repeat again? Like the electron rich can polarize the
Electron cloud of chlorine to a larger extent, hence inducing a dipole. You all know what's a dipole, right? Delta plus, delta minus.
So the carbon area is electron rich, is it?
Yep, the carbon-carbon bond is electron rich because of the pi bond. Because the carbon atom here is sp2, right? So if your sp2 means you are trigonal planar, so you are flat. The pi bond is formed from the sideway overlap of p orbitals. The pi bond is perpendicular to the flat molecule. So therefore, the pi bond is exposed to external surroundings. So as a result, they are electron rich. So I just want to make sure, guys, that you all are able to see that despite reacting the same molecule called chlorine, they have differing outcomes. Can you see that? Okay. Any questions? No, huh? Alright, so what we're going to do today is we're going to focus on the life cycle of a radical. And that is named in 3 steps. So guys, these 3 steps are not in chronological order. I understand that the lecture notes put steps 1, steps 2, steps 3, but they are not in chronological order. Let me explain why. Okay, so borrow your Starbucks. Okay, so guys, what happens here is that this is a closed system. All right, imagine this is a closed system, right? Okay, so you put in methane and chlorine inside this gas canister. All right, and it is open air. So not open air, it is transparent, so that UV light can pass through. Okay, so which means that I can just put this Starbucks cup outside and light can pass through. As light passes through, guys, okay, it causes, because UV light has a certain wavelength. A certain wavelength gives off a certain energy, because energy and wavelength is inversely proportional. Agree not? That amount of energy can be used to break the chlorine-chlorine molecule. The chlorine-chlorine bond in a Cl2 molecule. And this is known as initiation. Initiation comes from the root word initiate, which means to start. To start creating new radicals. So the words initiate, propagate, and terminate are referring to the life cycle of a radical. You all understand? Not? Are you all following so far? So when the UV light, guys, comes in, okay, when the UV light comes in and hits one of the chlorine molecule, the chlorine molecule will tear apart to give you chlorine radicals. Correct? Not? Now, you see, according to the syllabus, chlorine radicals are highly reactive species. Am I right? That contains an unpaired electron. So right now you have Cl radicals in here already, inside the same gas canister. And you still have methane, and you still have other chlorine radicals that are present. You all agree now, guys? Correct? Now, because they are highly reactive, they wouldn't know who they are going to collide against. They could collide with methane. They could collide back with the same chlorine radical that they broke apart with. Am I right, guys? Because it is random. It is in a sealed container. So we do not know where the chlorine radical will attack. Will he attack methane or will he attack another radical? When I say attack, the word attack means collide. Will he collide with methane or will he collide with another radical? And therefore, it comes up with two different terms, propagate and terminate. I'm going to start off with termination first because it's a lot easier. For termination, it is when a radical happens to collide with another radical. When a radical who has an unpaired electron meets someone who also has an unpaired electron, when they collide, they're going to form a what, guys? A normal covalent bond. Make sense? And that's why the step is called termination. Now, why do I say that this is non-chronological? Because termination can happen before propagation, or propagation can happen before termination, because we have absolutely no idea whether the radical that you produce in step 1 is going to collide with a molecule or is it going to collide with another radical. We have no clue. It's based on random collisions, you see. Does that make sense, guys? Okay? Clear? Alright? So, let me talk about propagation first. Okay? Now, so in the propagation step, this happens when a radical collides with who? With a molecule. When a radical collides with a molecule, right, the molecule will turn into a radical. So, let's take a look at what exactly happens. Come. If you take a look at my screen here, guys. Okay? I'm going to draw the arrow. Okay, drawing the arrow for propagation and termination is not in IB, So I'm just going to show you nevertheless. So you have chlorine radical, right? Okay? So look. As you can see, because of the similar electronegativity between carbon and hydrogen, the carbon and hydrogen bond is undergoing homolytic fission. Agree? Because of similar electronegativity. Then you might be recalling, but I said just now that the CH bonds cannot be broken because it's 413 kilojoules, correct or not? Am I right? I said that, right? So what exactly happens is this. When you form a bond, it's exothermic. When you break a bond, it's endothermic. So what they realize is that thanks to the UV light that is just happily passing through, right? Plus the bond energy, the energy release from the formation of HCl. Can you see that HCl is going to be formed? Alright, so the energy release from HCl plus the UV light will allow you to break the CH bond. Does that make sense, guys?
Wait, can you repeat that?
So you see, HCl, when you form a HCl bond, you release energy into the surrounding, correct or not? When you form the bond here, look here. When you form this bond, isn't this exothermic, guys? Correct? This exothermic reaction will be used to break the CH bond. This plus the UV light that has been coming into your gas canister can be used to break the CH bond apart. Understood? So as a result, this becomes a spontaneous reaction. So when CH4 reacts with chlorine radical, you are going to form a CH3 radical plus HCl. Can you see that?
Wait,
So the molecule will turn into a radical while the radical turns into a molecule. Like this. So your products will be CH3 radical. Correct? Plus HCl. Can you see that? Yes, your question.
Doesn't like the bond have to be broken first to
Yeah.
make the HCl?
Yes, the bond has to be broken first. But when Cl radical approaches H, what will happen to the bond length? It will start to lengthen. And when the bond length lengthens, what happens to the bond energy? It will drop.
Wait, why does the bond length lengthen?
Because the H wants to go to Cl.
Why? Oh, because it's more
Be-
electronegative.
Exactly.
Oh. Okay.
Can So this is called propagation. So the molecule will turn into a radical while the radical turns into a molecule.
Do you have to know that the bond length?
No need.
Oh, okay.
But students ask, how come this can happen? Because UV light can only supply X amount of energy. So how do you break the CH bond? Because you think about it now, we are screwed. If UV light can break any CH bonds, right, we are basically screwed. You know why? Because every day in the day we have the sun, right? Then all our organic molecules will be torn apart. When you drive the car, you think about it, it is organic molecules right in your fuel, and light passes through this fuel, they will start breaking apart. So you know that if UV light actually cannot break CH bond, there must be something else that is supplementing. You all know what supplementing, right? So UV light supplies a certain amount of energy. The bond form from HCl also supplies that amount of energy, and that allows him to break the CH bond. Are you all clear?
So it's the energy from HCl plus plus UV light.
Yes, correct.
But why would the CH4 want to react with the radical anyways?
Sorry again?
Like, why would the CH4 want to react with the chlorine radical anyways?
It's not that they want to react, but because it is in high concentration.
Oh.
Yeah, it is in high concentration, so the probability is there.
But on its own, CH4 is not reactive.
No, on its own CH4 is very, very unreactive. It's actually a greenhouse gas. Right? Yeah. Okay, so now you have propagated a new radical. Can you see your propagated in English? Propagate means what, guys? Make new, correct? No? That's the meaning of propagation, right? Yes?
Yeah.
So they have propagated a new radical, and this radical is now in the same canister as everyone else. Does that make sense or not, guys?
Yeah.
So now there's another radical there's another radical produced, and this particular CH3 radical can do what? Can go and react with another CH3 radical. There's one possibility, am I right?
Or just like anything.
And this CH3 radical can also react with Cl2.
It's only these two or anything.
This is these two only one. There's no other molecule that he can react with. He obviously can't react with methane, because when CH3 radicals react with methane, is literally the same molecule.
Yeah.
Correct? So he only has two options. When this CH3 radical that has been produced, he can either react with Cl2 or he can react with himself. Should he react with himself, he will be terminated, which means the radical will cease to exist. It will now become a molecule. However, should the CH3 radical meet another chlorine molecule, then what happens? The chlorine molecule will undergo homolytic fission, right?
Then there'll be more Cl radical.
And then there'll be more Cl radical. And guess what this Cl radical do? Go back to step 1 again.
Then they can be both propagation and termination.
Exactly. So are you all able to see that Cl radical is a what type of catalyst, guys? It is a homogeneous catalyst. Can you see that it gets regen or not in the second step?
Yeah.
It is used up in the first step and then gets regenerated in the second step.
Wait, but doesn't the homolytic fission happen all the time? When the CH3 radical meet another like Cl radical? That's what
Can, there? CH3 meeting another Cl radical.
No, but like CH3 radical. So it can be radical or non-radical.
Correct. We do not know who is going to collide with what. It's a game of probability what here. Right? There's actually more steps, guys. But your syllabus only covers up to mono substituted. You know what's mono substituted? One time only. So the chlorine atom, right, could keep on coming in, you know. And then eventually, what's the last molecule he will form? CCl4. But you all don't learn until then. So every substitution is 2 steps in the propagation, if you all realize. Okay? So do you all realize or not, this particular method of making a halogenoalkane is not very good. Why? Why is it not very good?
Because we can't control the product.
Exactly, you can't control the products. There'll be a lot of products and you need to do purification. And when you do purification to isolate the product, what happens, guys? You have to use a lot of solvents. When you use a lot of solvents, what happens? You are environmentally unfriendly. Your processes are environmentally unfriendly. Number two, the cost is very expensive. Right or not? Just for you to collect that very little yield of compound that you want, which is chloromethane, CH3Cl, you have to do so many steps. So free radical sub is not a recommended method in order for you to generate halogenoalkane. Okay, it is also written here, guys, in Chem Guide. Okay, where is it? They got mentioned about it. Later I will find it for you. They got mentioned about the fact that the radicals that is produced, okay, that free radical substitution results in multiple products, and because of the fact that it results in multiple products, the yield is very, very low. Okay?
It's used to produce what?
Sorry?
It's produced what? Like a C, then there's a halogen inside.
Halogenoalkane. An alkane with a halogen inside. Now, your X that you're referring to here, guys, your X that you're referring to here is only chlorine and bromine. Alright, and nothing more. You might be thinking, why not fluorine and why not iodine? Why must it be chlorine and bromine? Okay, it is because of the fact that for fluorine is a very, very strong oxidizing agent. He will oxidize the whole alkane molecule to carbon dioxide and water. So that's why we don't do free radical sub with fluorine. But for iodine, it is because of this, the propagation step. Just in case you want to know why iodine cannot be used, you need to study the go home to sleep equation. Now this go home to sleep equation is found in your data booklet, and that allows you to find spontaneity. Based on the reaction here, are you able to see there are 2 reactants and 2 gaseous products? And therefore your delta S is approaching 0 because you have the same number of reactants and products. So when delta S is approaching 0, temperature, the T delta S term becomes 0 as well. So your delta G, your spontaneity of your reaction, guys, is pretty much affected by your delta H. Understand not? Now the problem is this. If I replace this with the letter iodine, what they realize is when CH4 reacts with iodine radical, the reaction is endothermic. So this particular reaction here, the delta H is positive. And when it is positive, you go back to your spontaneity, you realize that it is a non-spontaneous reaction. So the energy release from HI is not sufficient to break the CH bond. So that's the reason why iodine is not used in free radical substitution. Clear on this?
Wait, why is T delta S almost 0?
Because delta S is 0?
Why?
Because there's same number of reactants and products. Have you all learned alkanes yet in school? No yet. Where you all at?
It's not the optical IC.
Sorry.
It's
Oh,
not the
sorry.
optical IC.
She doesn't even attend class.
She was born.
Oh, you born already?
I attended the last lesson.
Huh?
This it was about rice. Do you know what I'm saying?
Okay, are you all clear on this? On the processes? Okay, because later I'll make you all to write this out. The initiation step, propagation and termination. You have to do this for your exam. It's 4 marks.
With the equation.
The equations, yeah. The only time you need to draw arrow for this mechanism will be the initiation step. You do not need to do this, guys. These are not needed. Your job is to only write equations for propagation and termination. And this is also written as well here. Explain using equations the propagation and termination step in the reaction between alkanes and halogens. Alright?
Can you repeat why F can't be fluorine can't be used?
Because it is a very strong oxidizing agent.
Yeah.
It oxidizes all the organic molecule, the alkane rather, to carbon dioxide and water. Okay? Now, so the next thing that I need to teach you guys is to ensure that when you all leave this place, that you all don't think that free radical sub can only occur in alkanes. Alright? It can occur in any compounds that has an sp3 carbon hydrogen bond. So if you take a look at this particular molecule here, this is called propene, just in case you all didn't know. This is called propene. And propene, if you notice, is divided into 2 sections. The alkene section and the alkane section. Can you see that now, guys? So as long as you have an sp3 carbon hydrogen bond, you are capable of forming of conducting FRS. So let's start off, guys. If you take a look at your alkene molecule, you do realize that your alkene molecule is unsaturated because of the fact that he has a pi bond. Can you see the pi bond? So as a result, you have to ask yourself this question. Is it easier to break the pi bond or break the sigma bond? He has an option, you see. Unlike our dearest alkane who has no option, he can only break sigma bonds. Make sense? So because the alkane molecule can only break sigma bonds, he has to undergo sub, whether he like it or not. He has to undergo substitution. But for your alkene molecule, he has an option. Either you break the pi bond or you break the sigma bond. But breaking pi bond is a lot easier as compared to break sigma bond, right? So therefore, alkenes tend to undergo addition rather than substitution. Understood? For alkenes. So because of that reason, guys, when an alkene, when you meet chlorine in the presence of UV light, both addition and free radical substitution can occur because addition reaction is light independent. Got light or no light, it will still happen. Understand? Okay? However, when you add chlorine gas in the dark, right, only electrophilic addition can occur. Understood? Free radical sub cannot occur. So right now, last time in secondary school, when you were asked to distinguish between alkene versus alkane, you just say add bromine, right? The reddish brown bromine decolorizes, correct or not? Right now you must say add bromine in the dark. Why must be in the dark? To tell the examiner that you are aware that addition of bromine could also lead to free radical substitution.
What's EA?
Electrophilic addition.
Oh, electrophilic addition.
But I haven't teach you all yet. So I just say addition. I just tell you that it's addition reaction first. Because you all learn addition reaction in secondary school for alkenes, right?
Yeah.
Correct? Now, you might be thinking, how come, right, FRS cannot occur here? Okay? Why FRS can occur here but cannot occur here? That's because the CH bond here is stronger than the CH bond on the right hand side. And why is that so? Because this is a covalent bond. And the definition of a covalent bond is an electrostatic attraction between the nucleus and the shared electrons, correct or not? So the closer you are in terms of attraction, in terms of distance, the stronger the electrostatic attraction. When you are sp2, you have 33% s character, because sp2 means you have 3 orbitals, s, p1, p2, correct or not? S1, p1, p2, so you have 3 orbitals. So because you have 3 orbitals, that means that the percentage of S inside sp2 is 33.33%. When you are sp3, how many orbitals do you have? S, p1, p2, p3, right? So you have 4 orbitals. The percentage of S is 25%. So you have 33% here, you have 25% here. Correct or not? S is closer to the nucleus as compared to P of the same quantum shell. Agree? So if you have more S, therefore you are closer to the nucleus, and therefore your electrostatic attraction is stronger. And that's the reason why this bond here is stronger. And because this bond here is stronger, FRS cannot occur on an sp2 carbon hydrogen bond. Because UV light will not be able to break this. So they cannot undergo homolytic fission. Understood, guys? Can So the take-home message will be FRS can only occur on sp3 carbon hydrogen bonds. Clear? Okay.
FRS is free radical.
Yeah. Substitution.
Wait, because S is closer to the nucleus, so it's harder.
Yeah. S is closer to the nucleus, therefore electrostatic attraction stronger, right? And when electrostatic attraction is stronger, your covalent bond is stronger as well.
You can show the yeah.
No, you're not. No, but I feel like it's just my routine. My body is used to eating breakfast. That's why I was. No, not really. It's supposed to be breakfast.
Wait, but didn't you say like HCl before?
Fuel less energy.
Sorry, where?
For the FRS. So then what's this? Oh, because HCl is formed and the other Cl goes there. Okay. So it's like plus HCl, like that.
Yes.
Okay.
Are you right? I'll eat lunch. Yeah. What's that? You have 3? Always. Don't pay for lunch. Standard.
Okay, how? Can or not? Can understand? Alright, let's carry on. Okay? Next part will be classifying carbon atoms. Okay, so this one you need to listen because we will need it for the next chapter as well, chapter 11. I will also need to teach you all how to find chiral centers.
Isn't a chiral center just like 1 to 4 different things?
Yeah, but I noticed that for the past 3 lessons, because I already conducted 3 lessons already, right? You all get confused when they are attached to the same atom.
That's like different group.
Yeah.
So I explain. Oh, I explain that to the explain. When in chem class, was the years asking us.
Oh, you pay attention during Sergei's class.
Yeah.
We
Well,
do
actually,
the modeling
was
model.
super serious.
Huh?
Oh, yeah, because he gives us the model to play.
We're like the only group
Right, it's
doing
quite fun.
the model.
Oh, you're the only group?
It's
Yeah.
quite fun. You actually learn quite a lot playing with the model.
You as well.
I skipped
No,
those.
that is all.
Oh, you pawn ah?
Brother did not prepare for last lesson of the film.
Yeah, I forgot about chem. I just left
You
school.
forgot. You did not forget. You did not forget.
I thought school was over.
Yeah, then Sergey said it was screwed.
Huh?
Why?
So you said like, you just say our class damn bad, no one shows up for class, everyone's gonna suffer. Except for us. You and Casper.
Yours is so Kesiang don't bother, right? Okay.
There was once she skipped class and then she was caught.
No, I actually did get caught, but then he didn't.
He didn't recognize you.
No, he recognized me. He asked me why am I not in class, but I was walking away already.
You what?
I was walking away already.
You ignored him.
He just kept on walking. But he never asked me like again already. He never scolded me.
Okay.
And then the next day was his birthday. And then we wished him happy birthday. We were very happy. Then the next day, he treated us to drinks.
Oh.
Yeah.
Okay. So, I'm going to teach you guys how to classify carbon atoms. All right. So that you can be able to tell the probability as well of a chlorine atom coming in differing positions. What do I mean by that? When a radical, right? When a radical comes in, okay, there's a few possibilities of which hydrogen atom he would like to substitute. Correct? And that depends on the type of carbon atom that the hydrogens are directly bonded to. So this is called the reference molecule for alkane, which is called methane. And methane has 4H, correct? As you probably could tell. So I want you all to take a look at CH3. Now CH3, right, has 3 H's. Methane has 4 H's. So the number of differences is 1. So therefore, this is called a primary alkane. Okay? This one here is also called primary. Is that clear? Because it's also called CH3, right? So 1 difference. Then the next carbon atom, you do realize that he only has 1 H directly bonded to him. So there are 3 differences, so we call it tertiary. The next carbon atom, because of the fact that he has only 2 H's instead of 4, is called secondary. And the last one here is called primary. Understand, guys? Clear on this, huh? So since we already know, since we are already labeled, we now need to identify, are the primary carbons the same? So as you can see here, this primary carbon and this primary carbon is attached to the same tertiary carbon. So we say that the hydrogen atoms are in the same environment. What do I mean by the same environment? Same environment means if a chlorine atom comes in here or a chlorine atom comes in here, it's exactly the same molecule. You're going to form the same isomer. Alright? That's the meaning of the same chemical environment. Alright? However, if a chlorine atom comes in here, for example, you will form a different isomer. Means your products will look different. Clear? If your chlorine atom comes in here, even though he is a primary carbon, he is in a different chemical environment as these 2 primary carbons. And why is that so? Because the primary carbon in question is directly bonded to a secondary carbon. Understood? And because he is directly bonded to a secondary carbon, he is in a different environment from the 2 primary carbons who is bonded to a tertiary carbon. Are you all following so far? So therefore, guys, we can now start labeling our environments. So this is environment A. This is environment A because they are in the same environment. This carbon here is environment B. This carbon here is environment C. And this carbon here is environment D. Can you see that? So, because it's A, B, C, D, that means that should I substitute chlorine atom into this particular molecule, you're going to get 4 possible answers. Make sense? 4 possible isomers of each other. And the 4 possible isomers comes with differing probability. So if you go to environment A, because there are more hydrogen atoms, there are a total of 6 hydrogen atoms that can be substituted. Environment A has 6 differing ways in which your chlorine atom can come in. Environment B has only 1 hydrogen atom. Environment C has 2 hydrogen atoms, while environment D has 3 hydrogen atoms. Are you all clear? So what's the big deal about this ratio 6:1:2:3? It tells us if I want to substitute chlorine atom at environment A, the probability is 6 over the total number of hydrogen atoms, which is 12. So 6 over 12, the probability is 0.5. Should I substitute this chlorine atom over here at HB, this will be 1 over 12. If I were to ask you, what's the probability of substituting a hydrogen atom at environment D, is 3 over 12. Does that make sense? So all these numbers here, 6, 1, 2, 3, tells you the probability of substituting a chlorine atom or a hydrogen atom.
Shouldn't that be like D? Like D shouldn't be 1, is it?
No. D has 3 hydrogen atoms. What?
But A also.
Yeah?
A has 3 hydrogen atoms.
6. Because the two CH3 groups are the same. Because they are both bonded to the same tertiary carbon.
Okay, so the exam they'll ask you what's the probability.
Yes. What is the probability?
Would they
Yeah.
label the environment for you?
Sorry?
Would they label the environment?
No, you have to label it. That's why this worksheet I'm about to give it out to you guys teaches you like practices the labeling of the environment. And we need this for the next chapter, chapter 11, which is the spectrum, NMR spectrum. Okay? Clear? So if you notice, this particular chapter is very content heavy. Correct? Can Okay. If you all understand, so if they will ask you questions like how many possible monochlorinated isomers will be produced based on this alkane. So when they ask you something like that, the translation to that question will be how many chemical environments are the carbon atoms in? Make sense?
Why is environment D different from environment A?
Because environment A is bonded to a tertiary carbon, while environment D is bonded to a secondary carbon. So when they ask you how many isomers will be produced when this molecule is being mono-substituted a chlorine, they are basically asking you how many environments are there. That's it. That's basically the question. Clear? So when they ask you for number of isomers, they're asking you for number of chemical environments. You understand or not? You want to try another molecule that I drew for the Saturday class? This one here. I only draw 6 carbon atoms because your maximum number is 6.
What's 3A? Oh.
Environment A.
Oh.
So, could you all, how many isomers will be produced, guys?
2.
Very good. There will be 2 isomers. And in what ratio will you produce?
2 is
12.
6 to 1.
Okay, very good. 6 to 1. Can Simple not? Okay, now take the formative assessment worksheet for alkanes.
Can I see the diagram usually?
Which one? The one in black? Okay. We will need this again for NMR next chapter, okay guys?
I thought it was the last chapter already.
No. The spectral.
Is that the last chapter?
Yes, that's the last chapter.
No, it's second last.
Yes, this is second last. Come, pass around. You have it, right? Okay. The foolscap is here as well. The answer key also I attach.
So A plus quantity. First you go over the question.
This also she can do.
Huh?
You can pass her this question.
Too easy.
Yeah. It'll be too simple for her.
Only one has to change, so it's primary.
They'll be like, what the hell is this?
But she also couldn't answer the organic compound.
Oh, really?
It's so difficult.
Oh, the naming, ah?
Yeah.
Ah, don't bother.
BCH4 now it's like only
Maybe just like
only one
just do everything.
Yeah. Why?
Some of the other
Which one?
what's the halogenation?
Where?
Is that the UV light?
Yeah, the UV light one.
So is it just Cl and then
There's one.
No.
What? They
Reagents.
state the suitable reagent, limited Cl2.
limited Cl2?
Is it Cl or Br?
Yeah.
Br.
Br. It's limited Br2. You know why limited? No?
Later there will be more.
Yeah, because later all the hydrogen atoms will get
So
substituted.
they're technically the same, so they both will go in.
And UV light, right?
Yeah. Or heat. Both are accepted.
When they say describe the reaction, that means we just
It means write down the mechanism.
It's just like all the
The
equations,
initiation, propagation, termination.
right? So we don't have to write down equations, is it? Or we
You do.
Okay.
That's the answer key. Okay, turn back. So right now I'm ahead, right, of the school?
Yeah.
Okay, never mind. Let's not ask her. She doesn't know.
Yeah. But
Okay.
I don't know like in our class is still in other classes.
Okay. Kyla is which class? Ah? I
We
did-
still don't know.
Oh, okay.
Must you specify in the presence of UV light or just like
In the presence of UV light.
how does it be limited? Yeah. And it's like talking about stuff that we learned last year. What? Fission.
Wait, for termination, do we show all three? Because they only ask for to form X. Like to form. Huh? Okay.
I don't know. What question?
B.
Why did this way formulate like this? No.
Got more chips.
What's inside the snack box? Bueno.
How many?
What? Thank you.
He's flying away. You're not sure. Yeah. It's really sure.
I know.
You remember?
Yeah. But the travel buster joke.
Oh my god.
I don't know, you showed it to
It's
me.
really nasty.
The
What is that?
hot one.
Yeah.
You were the most.
The I
Just
see
like this
website.
shirt.
Yeah,
Huh?
yeah.
I should like this shirt.
I don't know, but it's too big for it now.
But I said that she like this shirt.
Oh. No,
That
I don't think it's my sister hates it.
She thinks you look cute.
Okay, no, she just thinks like that.
Yeah. Free radicals.
Wait, if it has 0 hydrogens, is it still tertiary?
There's 0. How many is supposed to have it? Originally? 4?
Yeah.
It has to be like
Cool.
8. Well, what are you doing?
Because like, wait, this one's carbon, right? This one here.
Yes.
But it has 0 hydrogens, right? Because this is
Where?
C, this is C.
Where?
This one.
In the ring.
No, this one here, the start of the ring.
Does it still count?
Should I just put 4 degree?
Why?
Because it has -4.
But then
Hydrogens.
usually the levels are for like single bonds, right? This one has a double bond. Maybe it's different.
Oh, that's true.
I'm so scared.
Because alkene, right? What's the compare? I don't know.
Audrey steps.
Yeah.
For explanation.
For termination, all three.
Wait.
Wait, for termination, is it all three?
Actually, what?
The reactions.
Wait, what do you prefer option B?
Should be, yeah. Wait.
Question B. Isn't it the initiation, propagation,
Oh
termination?
no, you don't need all. You just need to describe how to form X on propane. So like the
Isn't that
non-relevant ones.
propagation
Right?
only?
Oh shit.
Oh yeah, you don't even need the third one. I think.
No. So it's just propagation.
And initiation.
Termination so
Wow, she's going crazy on chips.
I
Kidding. I think I saw two by chips. I didn't really did this year.
Wait, do you bond
I mean-
bio?
How do you know?
Because I
Bond
also bond
class.
bio.
Yeah, there's a lecture, but like I'm not gonna learn anything.
You tell anybody, you tell the teacher.
No,
You just don't know.
I asked my friend to send me the QR code for attendance and my attendance.
Oh,
You need it?
yeah,
Wait, is your teacher Mr. Kai?
yeah.
Did he recommend you to buy the study guide?
I have to study guide.
Because he told you to buy it.
No, I just bought it.
But he
Is
told
it
you.
the one with like the box? A lot of boxes.
Wait, let me show you the picture. Later.
So actually when we describe, you just write.
The equations,
Oh,
yes.
so no words.
No words, yeah. How okay not?
I don't know how, like, if there's bromine, how do I know the environment? Like,
They start off with propane, what are you talking about?
wait, they say this structure of isomer of X.
Yeah?
This is one, like, this is one of the isomers.
Yeah, this got 2 bromopropane, yes.
So this is one bromopropane.
Yep, very good. So that's a structural isomer because you move the position of the bromine atom.
But they ask for the ratio.
Yeah, like the 6:2 or this one.
Hey, do we have to draw or can
So,
we
like, how many environments are there?
You can write equations, huh?
I don't understand, like, how to find the number of environments.
Huh? I thought we just went through.
No, but that's when there's hydrogen. Now bromine.
There's no bromine. They asked you for propane. Before the bromine was added, what's the number of environments,
Oh.
dude?
So just 6 is to 1 now.
2.
2.
Yeah. 6
Oh,
is to
yeah,
2.
yeah. And for this one, you know there's a C here.
Sorry?
There's a C here, right?
Where?
Here.
Yeah.
So, but since this is an alkene, what's the reference molecule?
Huh? What are you talking about? There's no there's no what do you call it? There's no chiral center on sp2 carbon.
Oh.
For you to be chiral, you need to be sp3 bonded to 4 different groups. What?
Oh yeah, they're coming with the stereoisomer. Oh.
Ah.
Wait, but the NH, the H cannot spin.
Sorry again?
Like on the NH, the H cannot spin.
Can. But they ask for chiral carbon, not chiral nitrogen.
Not like for the last question.
Why?
What is the last question?
What last question?
The question B.
Why?
Like I know there's like you can turn the first carbon and the second carbon, but the H connected to the nitrogen can spin also or not?
Cannot what? The H bonded to the nitrogen can spin.
Like can what? Because it's not confirmed.
Yeah, we are dealing with configurational what? So this is one isomer, the one group. This is the second group. This is the third group. Then the big group is the fourth group what?
Oh, okay.
Correct?
Yeah.
So there are 2 chiral centers, right?
Yeah.
Yeah.
Impossible is 4.
Yeah, because it will be clockwise, anti-clockwise,
Oh.
anti-clockwise and clockwise, and then the last one anti-clockwise, anti-clockwise.
So
So
which
4.
is square?
Yeah, 2 to the power n, not square.
Or 2 to the
2 to the
power
power n, where n represents the number of stereoisomer. That's why I need to do the next worksheet with you guys. Because I don't think you all caught the... Like you all understood, like last week was the theory, right?
Yeah.
But I don't think you all had like hands-on practice on it. That's why I need to move on to the next worksheet after this. Faster.
How many questions? Oh, okay then. Number of stereoisomers displayed.
So it's for 1D, right?
Yeah.
The answer key to the last equation, but the last equation doesn't form X. Why are you doing
Where?
that? For
No, it does,
termination.
it does. No, it does.
It does.
This one.
Yeah.
Does this one.
How about this?
Oh, this one, nothing but it.
No, but it's only both.
So is this a diastereomers?
No.
But this is two bromopropane.
Ah.
Yeah, this one's
No need.
This is the thing that
They didn't ask all those questions.
Name the type of stereoisomer displayed.
Enantiomerism lah. Or optical isomerism.
Oh.
Oh, wait, 3 equations.
I guess mean the last equation for termination. Like what? There isn't even a bromine in there.
Yeah.
But
Because you produce this radical, what?
yeah,
This
but
radical could collide with himself, what?
doesn't the
But
question
then that
ask
doesn't form X.
the mechanism for reaction to form X?
Yeah, to form X there. This is the reaction to form X, but you have to write all the equations. Ma.
I have to write all 3.
Yeah, you have to write all 3.
Oh.
Yeah.
But I think if you put limited, that means like,
Yeah, there'll be no di substituted or tri substituted
Oh.
bromine.
Okay.
I attached the answer key right to the back for you guys.
Yeah.
Okay.
Yeah.
The fuck, how do you do 3A?
Huh?
3A.
They asked for the relative proportions.
Oh, you see, you have
The
oh, you have to, okay.
the 612, you know, the
Yeah, yeah, yeah.
environments. Yeah. There's a typo there for 4A. Is chlorine. Not that it matters. Lah. Cistrans and chiral centers. Basically, essentially last week's lesson.
Yeah, that's right. That's right. It's basically, let's say you have this, right? Then this collides with itself. This is all the possibilities.
Possibilities of the different radicals meeting each other.
Yeah.
So So 6, 1, 2, 3.
Yep, well done.
Type of reaction, isn't it just substitution?
Sorry?
Type of reaction.
What type of reaction?
You should name the type of reaction between 2-methylene butane and bromine.
Free radical sub.
Oh. Isn't that free radical sub for everything?
Yeah.
Is it a structural?
Sorry again?
Is it structural isomer?
Yes. No, it is cis-trans isomers. Right?
No.
They say in P what? They just say in P. What does P have?
Oh.
Yeah.
Cis-trans. But there's only 3 though, it's not 4.
What do you mean 3?
Or it just needs 2 opposite ends. No.
Cis-trans is not the same as enantiomerism, yeah?
It's the thing where like
Across the carbon-carbon double bond,
It's
there
the
is
same.
similar groups, yeah.
so
Mm.
CH3 CH3.
So if you notice over here, there is similar groups, right? Across the carbon-carbon double bond, which is hydrogen. So therefore cis-trans. So if you were to draw out, CH3 and then CH3, right? Correct? And then this is trans, correct or not?
Yeah.
Then the other way will be
Oh, like that, right? Okay. Then.
Can you explain the answer for once?
they ask you for the ratio, right? Then so this is cis or what?
Can you explain the answer for once?
There. So there's a line of symmetry. So you first label the different types of carbon atom, primary, secondary, primary. But the primary carbons are identical because they're both attached to the same carbon. Agree, no? So therefore environment A has 6 hydrogens, environment B has 2 hydrogens. So hence the probability will be 6:2, right? Correct, not? Yeah.
Can I explain to
So you have 2 chiral centers, right? You managed to get the 2 chiral centers. So 2 chiral centers means 2 to the power of 2, where is 2 to the power of n, right? Where n represents the number of stereoisomers, correct? Because when you have 2 chiral centers, they could be rotating in a clockwise direction, and then one is clockwise and anti-clockwise, clockwise, and the last one is anti-clockwise. So therefore, that's 4 possible combinations. So hence 2 to the power of 2. The formula that you all need to know is 2 to the power of n, where n represents the number of stereoisomers. Correct or not? This was covered last week, right? The video also showed you that this particular formula was repeated itself. Stereoisomers consist of cis trans, your EZ, and the last one is your optical. So you have to add them up and then sub in into n here. So that will tell you the number. Okay? So because of the fact that we have 2 chiral centers, so you have 2 to the power of 2, which will give you 4 different stereoisomers.
It's optical.
Huh?
It's optical.
Yeah, because this is optical isomers are the same as enantiomers, right? They are used interchangeably.
Is it halogenation?
No.
Or free radical substitution?
Yeah.
But what's the difference between halogenation and...
The halogenation no longer accepted at IB.
Oh.
Because halogenation can mean 3 things. It could be free radical sub, it could be electrophilic addition, it could be electrophilic substitution. Which one is it?
Okay.
All 3 organic compounds can react with halogen.
Okay.
You understand? No?
Yeah.
Yeah. Are you all done already? Not yet? Oh. Faster, I need to move on to the next worksheet.
Then the equation is initiation.
Propagation, termination, yeah.
Metal butane is C4H10.
What?
It's CH3. Metal
No.
butane.
This one is methyl propane, right?
But they asked for metal butane.
Oh, so this is the typo lah.
Oh.
Yeah. Ethyl, propane, and chlorine.
So C3H8.
Huh? No. C4H10.
Or just C4H8.
Yeah.
Isn't that just butane then?
Yeah, but it's a structural isomer of butane, so it's got 2-methylpropane. Mm. Hey, you done already? Okay, good. Come. I pass to you. Sorry. Are you done with it? You have already, right? In the soft version,
Yeah.
right? Now for the three of you. Yeah. Correct? We need to go through that worksheet. I will teach you all first. Then you all go back and do as homework. Because we have the next time I see you will be next week, right? I don't have any lessons anymore with you. So I will start off next week by going through the MCQ of that particular worksheet. But I need to go through some questions with you guys so that you will know what in the world I'm talking about.
So if there's like nothing drawn, then is it like
CH.
okay?
Yeah. Each carbon, you must always remember each carbon atom can only form 4 bonds.
Is it the intro to organic chem questions?
Yes. Okay, I shall switch to that. Once you're ready, y'all just turn to that particular question, okay?
Which question?
No, as in I will go through like about 5 questions. Like the first page I want to go through, then after that, y'all do the rest. There's about 22 questions on finding chiral centers.
Oh, you don't really know that. You just know that it forms. No, I just drew this one. I just wrote it up.
done? Yeah, that's why I'm waiting for them. You move on to 3 first, lor. Then? Okay, ready? Sorry. Okay, so guys, if you take a look at question number 1, I'll go through the first page lah. Okay, then after that you have plenty of questions. Go and find chiral centers. Okay, when they ask you how many stereoisomers are possible for the following molecule, your job is to go and write down that how many cis strands as well as how many enantiomers are possible. Clear? So, the chiral center one. Okay, so you start. Which one you want to start off first? You want to start cis strands or you want to start enantiomer first? So you go to the molecule. I always start with cis strands because it's easier to find, right? So you go to all the carbon-carbon double bonds. You'll understand now, guys. Alright? Now you start off with the very, very first one on the extreme left. Are you all able to see that the one on the extreme left, the carbon atom has how many hydrogen atoms? 2 attached to the same carbon. That's not right, what? You need to have 2 differing substituents on the doubly bonded carbon atom. But what happens here is, he only has how many? He has 2 attached to the same carbon atom, so cannot. So therefore I put a cross. Are you all clear? Now you move on to the next carbon-carbon double bond. Are you able to see that the hydrogen atoms are on opposite sides? Yeah, so this is in a what configuration, guys? Trans. Very good. Okay, this is in a trans configuration. The next one over here. This is not cis trans, yeah? Clearly. This is actually EZ isomerism. Why is it EZ? Because there are no similar groups across the carbon-carbon double bond. Because for you to have cis trans, you need to have similar groups, H and H. Right? You need to have similar groups across. This one don't have. But that doesn't mean that he cannot be classified under this type of cis trans isomerism as well.
Wait, but I thought EZ is not tested.
The naming is not tested.
Obviously we have to.
Yeah. You just need to be able to identify. You need to point that this one is also a form of cis trans isomerism as well. So guys, this one here, each doubly bonded carbon atom has differing groups. Can you see that? 1, 2. Correct or not? The same thing over here. There's a hydrogen here, which I didn't draw. This is a hydrogen. So 1 and this big ass group. Correct or not? 2. So therefore, this is another form of cis trans or EZ isomerism. So grand total there are 2. That's why I put 2 in front here. Next, for me to find enantiomers, I need to find chiral centers. Correct or not? And what's chiral center, guys? sp3 carbon bonded to how many groups? 4. So now, again, no point looking at this, no point looking at this, or any of these carbon atoms. Correct or not? Why is that so? Because they're all sp2. Agree? So therefore, there's only one chiral center here, and another chiral center over here. Can you see? Red and green. This one is not a chiral center because the groups are the same. That's why not chiral center. So grand total, 2 plus 2 will give you 4. Hence a grand total of 2 to the power 6, a grand total of 16 stereoisomers in this molecule.
The other chiral center.
Sorry?
Where's the other?
Can you see? 1 group, 2 group, 3 group, and a huge molecule is the 4th group.
Why is it 2 plus 2?
Because 2 stereoisomers, 2 cis trans and 2 enantiomers. Yeah. Is this okay, guys? How fun? Not? No.
No.
You don't like this chapter?
Very content heavy.
You prefer electrochem?
I think electric comes better than this.
Acid base?
I don't like
Acid base painful, right?
Yeah.
The PH one.
Yeah. Actually, the year 6 topics are hard. Okay. Now question 2. Question 2 is inorganic reagent, right, guys? What's the definition of inorganic reagent? Non-carbon containing or they are ions. Understand? Clear? Organic molecules, are they covalent or ionic?
Covalent.
Very good. So if you're not covalent, you're considered an ionic compound. Therefore, you are inorganic. Understand? Okay, now let's start off with the very first one, guys. Option A. The inorganic reagent is bromine, right or not, guys? I drew the electron cloud. Look up. I drew the electron cloud of ethane. And the electron cloud of ethane doesn't polarize the electron cloud of bromine to such a large extent. So what type of fission does he undergo, bromine? Homolytic fission. So as a result, you produce 2 bromine radicals. Understand? So the inorganic reagent here is a radical. They want the inorganic reagent to be what? A nucleophile. Once you realize it's a homo fission, you know that you're not going to get your nucleophile, neither are you going to get your electrophile.
So it's just C because there's a double bond.
Sorry?
It's C because there's a double bond, is it?
Where?
Answers. Yeah, for 2.
For 2, ready? For number 2? Okay, for number 2, guys, I want you all to focus on the inorganic molecule, which is circled in red. So can you all please draw your dearest Lewis structure, okay, for nitric acid. Come, draw the Lewis structure for nitric acid. Okay? Alright, let's take a look. Now, if you take a look at nitric acid, are you guys able to see that the nitrogen atom is delta positive? Now, why am I so focused on the nitrogen atom? Because I want you to focus on the products, yeah? C6H5NO2, which means that the nitrogen atom is directly bonded to carbon. Can you see that now, guys? So that's why I am very fixated about nitrogen, because I want to know what nitrogen is. And nitrogen is flanked by 3 electronegative oxygen atoms. That makes him very, very delta plus, right? Correct? Benzene, if you still recall your resonance that I taught you earlier in the year, in January, under chem bonding, you do realize that benzene ring is an electron-rich molecule. So benzene is a nucleophile, albeit a poor one. Right? Can understand? So, this nitrogen atom that we are looking at here is delta plus. What is delta plus, guys? Electrophilic or nucleophilic?
Nucleophilic.
Sorry? It is electrophilic. Alright, why is it electrophilic? Delta plus means you're lacking electrons. And why are you lacking electrons? Because all the electrons run away from you, right? And why did they run away from you? Because you're bonded to 3 oxygen atoms. Understood? So hence, because of that reason, guys, HNO3, the nitrogen in HNO3 is electrophilic. Clear? Because they asked for the inorganic reagent one, right?
Yeah.
So we should focus on the nitrogen atom. Do you all agree now? Because it is the nitrogen atom that got attached to the benzene ring down. Just in case you all are wondering how they got attached, is like this. See? The benzene attached to nitrogen with double bond O and a dative bond towards oxygen atom.
Why is there a circle in benzene?
Sorry?
Why is there a circle?
The pi electron cloud
Oh.
formed from the sideway overlap of p orbitals. Okay, clear? Alright, next. Option C, guys. Okay, so for option C is an alkene, right? As I've already mentioned, when alkene approaches chlorine molecule, because it's electron rich, what type of fission will occur?
Hetero.
Hetero. So therefore, there'll be a delta plus as well as a delta minus, correct? Do you all agree? So now, the question is, you're going to form an electrophile as well as a nucleophile, right? Do you all agree?
Yeah.
Okay, so let's label. Since you all already agree, right? This is an electrophile. This is a nucleophile. Correct or not, guys? Yes? Now my main question I want to ask you. So is it electrophilic or is the inorganic reagent electrophilic or is it nucleophilic? Because he has both. Yes? So to answer that question, you need to take a look at the first step or the slow step. Will the alkene react with the electrophile first or will the alkene react with the nucleophile first? Make sense? So you ask yourself this question, will the alkene react electrophile or will he react in nucleophile? We already disrupt alkenes as electron what? Poor or rich?
Rich.
Rich, correct? And because the alkene is electron rich, he will not react with the nucleophile first. He will react with the electrophile first. And therefore, the inorganic reagent is electrophilic. Because the slow step or the first step of the reaction involves adding the electrophile first. After he has added the electrophile, the second step, then they will add the nucleophile. You will see this reaction next week, the mechanism.
But like, it's still nucleophile though.
No, the name of the mechanism follows the slow step of the reaction. Wait okay, sorry. Okay, done. Okay, and the last one. Okay, the last one is K plus and just in case you all didn't know, KCN is an ionic compound. So it's divided into two, K plus and Cn minus. Can you see that? Okay. So the inorganic reagent, K plus you all know that is neither a nucleophile nor an electrophile. Why? Because if you write out the electronic configuration, he is neither electrophilic nor nucleophilic. Because he has a full electronic configuration, correct or not? K plus, right? So you need to focus on Cn minus. Are you guys able to see that the Cn minus replaced the Br minus? Yeah, based on the product. Can see not, guys? On the left hand side, there's bromine. The bromine got replaced by cyanide. Can see that? So Br minus left for Cn minus to come in. So I drew out Cn minus for you. And are you able to see that the lone pair on carbon is the one that is responsible for donating the electrons? Okay? Now you might be thinking, why is it carbon that donates the lone pair? Why not nitrogen? Nitrogen got lone pair. What?
Nitrogen is more electron.
Yeah. Nitrogen more electronegative. So they cling on to their electrons more tightly. So it's usually carbon that gives up the electrons. So carbon makes fantastic nucleophiles. Alright? Now, last question, okay? Last question. Then after that, you all can do it. Try to do it and on your own. Now, you all might be wondering, why am I so fixated about tertiary carbon, secondary carbon, primary carbon? It is because of this example, or the future examples that you're going to see. They ask you to find chiral carbon. So I'm going to start with citric acid first, yeah? Okay? Because it's easier, because it's not a ring. Now, citric acid, are you able to see that there's only one carbon that is sp3? The one in the middle. The one in blue. The one that I highlighted with a dot in blue. That's your sp3 carbon. Do you all agree? Everybody else is sp2. All the carbon atoms in citric acid are sp2 except for the blue one.
How come the one right next to the blue one is not?
Yeah, but the sp3 carbon is bonded to 2 hydrogen atoms.
Oh,
So it's not chiral. Correct or not?
Yeah.
Neither is the one that I highlighted in blue. And the one that I highlighted in blue is not a chiral carbon because are you able to see the 2 circles or not? I circled in blue the 2 groups that looks identical to each other. Because for you to be chiral, you need to have how many groups, guys? 4 different groups. He has one group that is different called OH. COOH also different. But the problem is these 2 groups are identical to each other. This and this are identical, right? Do you all agree or not? These 2 are identical.
Yeah.
So therefore, the chiral center, the carbon atom that we thought is chiral is actually not chiral at all. Are you all following not what I'm saying here, guys?
So there's nothing.
So the chiral center 0 lo? Citric acid has no chiral centers at all. So need to be very careful, yeah? Okay, let's move on to estradiol. Now, to find chiral centers, you immediately eliminate the benzene ring because the whole benzene is sp2. You understand? No? Alright, now you just focus. Okay, guys, I don't bother about these carbon atoms because they are attached to 2 hydrogen atoms. You can't be chiral. For you to be chiral, you need to be bonded to 4 differing groups. So I look out for the intersections. Can you see the green points? Can you see the intersections? The intersections are where you find your chiral centers. But based on lessons like I covered over the past 3 days, right? A lot of you think that the carbon atoms are the same. So I'm going to start the pink one first. So this is a carbon atom, right? Correct? This is a carbon atom, but this carbon atom is secondary. Do you all agree, no, guys?
Yeah.
Secondary carbon. This one here, the one in the middle, like this is a what type of carbon atom, guys?
4 degree.
4 degree. We call it quaternary. Alright, this is a quaternary carbon. Are you all clear? And then wait, haven't finished. So the 2 carbon atoms are clearly different because one is a secondary, one is a quaternary, right? Then after that, this is another group called OH. Where's the last group, guys? The last group is H. They didn't draw. Okay? So as a result, this particular carbon atom is chiral. Okay?
So chiral must be tertiary at least.
What do you mean tertiary?
Like
For the ring, yes. Must be tertiary, lo.
yeah, or quadrant.
Or quaternary, yes.
Wait, so where's the chiral?
This one, no? This is a chiral carbon.
Oh, because it's the OH.
OH, H, secondary carbon, quaternary carbon. So that's 4 different groups already. Okay, then the next chiral carbon is this. Because it is a CH3, correct or not? Yes? And then this one is a what type of carbon, guys? This is secondary carbon, right? And then to the right of him is a tertiary carbon, right? And then to the bottom is another tertiary carbon, correct or not? But the tertiary carbon is different from that tertiary carbon below. Why? Because the tertiary carbon got OH group. The tertiary carbon below don't have. So that's the reason why they are different. So to make life very, very easy for you, right? Just go for the intersection points. The intersection points will give you your chiral center.
So see the Y.
Yeah, see the letter Y. That's why I draw the letter Y. The letter Y will give rise to your chiral centers.
Then this one is the chiral center.
Where?
This one.
Of course. Oh, damn it.
Every single one.
Every single Y, yeah. But this Y cannot, huh? This particular letter Y cannot, huh? You know why, right? Because this is sp2. Clear? Damn it. Bloody rain. Okay? Why? I haven't. Oh, hey, so how many chiral centers do we have, guys?
5.
5. Can? Oh, it's a passing rain. Huh? Okay, your homework for today, for next week's lesson, will be the MCQ questions. Okay, what we're going to do next week, no need to go to structured, don't bother. Alright, just stop at MCQ because that's more than enough. So the MCQ questions, be it, just leave it there. Just leave the food there. Nanti saya kasih. Yes. Now, the MCQ questions, just do the MCQ questions for next week. If you all want to practice some more, you can go ahead lah. Alright, but the compulsory is to do the MCQ questions. Is that clear, guys? Now, I will give you all the answer key so that you all can check, and then after that, we can go through these questions next week. Is that okay, guys? Can?
Yeah.
Okay.